Okay, so we're VO2 Mask. I'm Bree.
I'm Jaskaran. And I'm Chai.
And we're just going to tell you a little bit about what we're doing so far and what our project's about. Next one. So I know last quarter they presented on VO2 Max, and they showed the whole machine and everything. We're actually kind of doing something similar but a lot different. Will be explained during the need part. But basically what we're going to be doing is just measuring CO2 and O2 on the ingoing and outgoing breaths, as well as activity levels. We'll be sending this to a phone app over Bluetooth, and you'll be able to see that. And then also the data is going to be sent to an SD card for the doctors to pull the data into Excel.
So we'll be working with Professor Ghiazzi and Dr. Brown. And Dr. Brown is a thoracic surgeon at UCD Med. And so she actually performs lung resection surgeries on patients, which is actually removing a piece of the lung. So before they do the surgery, the patients go through a bunch of tests, and one of these tests is the VO2 Max test. But the thing about the test is that it's physically intensive, and you need a bunch of equipment, and it just makes it hard on patients. So we're going to make a better way, or we're going to make a mask that will either supplement this test or replace it. So the mask that we'll be using will measure O2 and CO2 levels on the patient's respiration. And Dr. Brown will use this mask later down the road for more research, but that's our main goal for now.
So for our components, we had to be a little bit picky about the sensors we choose. Most sensors out there are for environmental sensors, and they detect small changes in a controlled area, but for the human breath, oxygen levels is on average around 16%, and CO2 levels on average about 3.6%. So then our sensors... 3.6? Yes, 3.6% of carbon dioxide. Okay. Yeah. So for our sensors, our oxygen sensor can detect up to 25%, and our carbon dioxide sensors actually goes up to 100%, which basically because that's average on rest. But if you have somebody exercising, it can go up to around like 10%, 8%, around there. Yeah. So the sensors we looked at either went up to 0 to 5%, or it goes up to 0 to 100%. Yeah.
So the CO2 sensor is a non-dispersive infrared sensor, and so this works by an IR light or IR lamp shines a light, and the CO2 absorbs some of that light, and the light that isn't absorbed is absorbed by the optical filter, and then the detector determines the difference between the the light radiated and the light absorbed, and from this we determine how much CO2 molecules are in the air. And the oxygen sensor uses fluorescence quenching, and this is also done by oxygen being excited by a LED, and the sensors produce a light that is detected by the sensor, and based on this, we know how much oxygen molecule.
LED doesn't excite the oxygen. LED excites a chemical that is responsive to oxygen.
Okay, yeah.
It's the chemical that's fluorescent.
It's like yeah.
Okay. So this is our mask design. It was hard for us to try and 3D print anything because of the nature of it being on your face. So we decided to use an elevation training mask. I don't know if you've ever seen them. Chai has like the part that goes inside. So we'll be placing the O2 and CO2 sensors on the two holes on the side, and then one in the middle. And the middle one will be for free airflow, and then we plan on placing the PCB on the side of the mask.
So for our hardware communication, we have an accelerometer for activity. We have oxygen sensors going through UART. And last minute, we actually added an SD card here to capture the data. So for our signals, our accelerometer is going to I2C. Oxygen and carbon dioxide sensor communicates through UART. And the SD card reader, I haven't looked too much into it, but I believe it is SPI. One thing that we're considering is we might need to add a PSOC 5. We're trying to implement this with just the PSOC 4, but the PSOC 4 is running out of communication resources because of the sensors we have. So we might need to add the PSOC 5 to this as well.
Okay, and then for the state diagram, it'll start off in the searching phase, and once it's connected, we'll be in the low power state. And it's not until we actually get, so it's not until we actually,
Want to read.
yeah, want to read that I'll go into the active state. And like, depending on how we time it, when we want, how often we want to take readings. Yeah.
Read.
Oh, yeah, sorry.
Booster converter.
That's how it was labeled in the data sheet.
Well, that's a good reason. Don't make the same mistake over.
So we currently have a 9-volt battery on our prototype because we had a flow sensor that needed 10 volts, but we're switching. We don't need the flow sensor anymore, so we're switching to a 3.7-volt battery. It'll be regulated to 3.3 volts, and that'll go to the SD card, PSOC, accelerometer, and CO2. And then we'll use a boost converter to power our O2 at 5 volts.
Yep.
Yeah. So our power calculation, do you want me to go through it? Or?
Oh, to 4 decimal points. That's really.
You gotta be very exact. Yeah, I think, okay. So we calculate that it should last about 18 days without a recharge. The math is up there. I don't know if you want me to go through it in terms of time. Okay. So this is our dummy app. We have an app working, actually reading in data right now. We want to move it to look like this. Yeah, it's pretty self-explanatory.
Yeah, the total price is $337.
It's rather expensive because of our sensors. Our sensors are pretty expensive.
Okay, you guys need to be out of here. So,